for this week. Take us 2 days to cover it. Section 1110. That will be the one that your test on Monday will be up to. So the next section, which is actually called applications, will be moved to the next 2 weeks. So up to this Sunday, you need to get 1110 finished. Okay, so that's your homework assignment is now finish 1110. And let's look at it. It's to do with power series. There are 2 special families of power series. They're called Taylor series and Maclaurin series. And we're going to start with Maclaurin series. And essentially, a Maclaurin series is just a power series of a function centered at 0, right? So it's going to be the power series that has the x to the n's in it. And what Maclaurin discovered was exceptionally cool, in my opinion. He found out that if you have a normal, well-behaved function, so we're talking about every kind of function that you're likely to meet that doesn't have too many weird things going on. So, you know, sine x, e to the x, x cubed cosine x, anything like that. Just normal kind of up and down curvy functions. Perfectly cool with that. Even functions that aren't totally perfect and well-behaved, Maclaurin series works. And he discovered how to find the power series of every function in the universe. And this is it. For any normal, well-behaved function, f of x, this is its power series. It's the nth derivative of this function evaluated at 0, x to the power of n, all over n factorial. So this notation you haven't seen before, f with a funny little bracket n of 0. Essentially, the reason we need that is there's f dashed of 0, right? We're okay with that. There's the double derivative at 0. Can you imagine finding the third derivative at 0? But it gets a little bit, you know, what's the 43rd derivative of? Would you agree that that notation really doesn't work well? So what we do is we do this. That would be the 43rd derivative. So you can imagine differentiating something 43 times, right? One after the other, and then evaluating it at a nice number 0. And when they do the n, well, that's basically when n is 0, when n is 10, when n is 20, when n is 42. So let's find the Maclaurin series for e to the x. So far, so good. Right, so let's start. The reason I chose e to the x is that you can't get any easier as far as its derivative is concerned, because aren't all the derivatives e to the x? Which means that won't the general nth derivative also be e to the x? And won't the nth derivative evaluated at 0 be e to the power of 0, which is 1? So far, so good. Now, Maclaurin's series, the power series of f of x, is sigma n equals 0 to infinity, the nth derivative at 0, which is 1, x to the power of n over n factorial. Well, nobody would say 1 times something. Wow. The power series for e to the x. Now, there are restrictions on power series. Most power series, well, all power series, have a radius and an interval of convergence, right? Which are the values of x where the power series actually works, right? And for some power series, they work like everywhere. And for other power series, you can only do numbers, say, between -1 and 1, which is a very common interval. Let's find out what this one is. So I'm going to use the ratio test to find the radius of convergence. And turn the other guy upside down. This guy cancels out this guy and leaves an x. This time I'm going to do the cancelling right now. There's an n factorial on the top, and it will cancel most of n plus 1 factorial on the bottom. But there is something left behind. Agreed? What do you get if you cancel an n factorial on the top with an n plus 1 factorial on the bottom? What do you get left over?
N plus 1 on the bottom.
And there's an x on the top. Now, what will happen as n goes infinite? Well, isn't x considered just a fixed number? It's a constant. So won't a number over infinity, I'm just brute forcing this, won't this number over infinity be 0? So the ratio test says that the limit of this particular fraction is 0, which is very good news, because won't you converge as long as the limit is less than 1? And this is a very special case, because no matter what x is, since the limit is 0, no matter what x is, won't it always converge? So that tells me that my radius of convergence is infinity, and that my interval of convergence is everyone. Which says that this particular power series, is unique for E to the x. That's the only power series for E to the x. And you can use it for any value of x you like, and it'll work. So let me write down e to the x in some of its terms. If you plug in 0, you get a really weird one, and I'll come to him in a minute. If you plug in 1, if you plug in 2, and lastly, if you plug in 3, obviously it goes on forever. That's what the infinite polynomial would look like. Now, this one here is weird. So I'm leaving him for a minute. That's just x over 1, which is x. That's x squared over 1 times 2, which is a 2, so basically a half x squared. And 3 factorial is 6, plus a whole load of other terms. Right, now let's figure this guy out. What number is x to the power of 0?
1.
Less obvious. What is 0 factorial?
1.
That did not surprise that person. Well, it seems unlikely or unreasonable, but it is 1, and it's one of those pieces of magic you're just going to have to accept, right? If you really want to find proof of it, go looking for a function called the gamma function. It looks like that. It's a Greek letter, capital gamma. Right? Gamma is that guy when it's small, but when it's a capital, it's that. And if you're interested in finding out why 0 factorial is 1, look up an article on the gamma function, and it'll take you into the depths of math where you can do it. So this is e to the x. Now, the reason why I'm writing this guy down is that I would like to be able to find a numerical value for e to the power of 0.02. And I am going to do it by finding the value of this fella Now, technically, the power series goes on for infinity. But one of the cool things about it is, do you know most of the value is in the first 3 or 4 terms? See the terms that come later? They're tiny in comparison, right? They hardly make any difference. So if I wanted an approximate answer, right, a close to, this should do it. So I'm going to calculate this and see what we get. And then I'm going to put this guy into the calculator and find out what it is. And let's take some bets. Do you think it's going to be good to 1 decimal place, 2 decimal places, or even better? How many think it's only going to be good to 1 decimal place? Little thumbs up. Any 1 decimal places? I'll put you on the big screen so I can take a head count. Oh, none of you. Okay. 2 decimal places. Do you think it's going to be good to 2 decimal places? In other words, this and that are equal if you round them off to 2 decimal places. I don't need to. Oh, okay, we got 1. Thank goodness we got a vote. Okay, so I'm assuming that everybody else thinks it's going to be better than 2. Or you haven't a clue, so you don't want to vote. Okay, let's find out how good it is. Clear this out. And it's going to be 1 plus 0.02 plus a half, which is 0.5 times 0.02 squared, plus 1/6 times 0.02 cubed. And the answer that I have is 1.02020133. Okay. Now, e to the power of 0.02 is, I'll write it underneath, 1.02020134. Oh, come on, you got to be impressed by that. I can take a function, e to the x, which doesn't look like a polynomial. I mean, e to the x, in my opinion, doesn't look like a polynomial, right? E to the x looks like that. Don't polynomials look like that? Yeah, this polynomial behaves identically mathematically if you took it to an infinite number of terms, exactly like that. Now, the reason I chose a value of x that is very close to 0 is because in Maclaurin, right, you're centered at 0. So it's very good with only a few terms as long as you stick close to 1. But if you try and use just 4 terms, but you use an x like 57, right, e to the power of 57, do not expect 6 decimal places accuracy, right? You need to do maybe 200 terms, and then it would be good. I think that's pretty clever. And I have no proof of this, but I believe I'm correct. How does the calculator calculate the value of e to the power of anything. You never thought about that. How does a calculator calculate e to the power of 2 or e to the power of nothing 0.1234? How does it do it? It's programmed a Maclaurin series. So when you ask for 0.2, it's got a power series there, and it just calculates it. Now, you don't see it happening because it's really fast, right? Electronically, you can do 1 million calculations in like 0.1 of a second, right? So can you imagine you could do 500,000 terms? And if you're into program, do you know it's quite easy to program this? Can you imagine you just do a loop and keep adding a term until you get to the accuracy you're looking for, and then you pump it out as an answer? So I can't say we're under the misapprehension, that's probably too strong a word, but isn't there now 2 ways to look at every function in the world? Like sine x, cosine x, e to the x, even combinations, x cubed sine x. We can look at them as they exist, but can't we now look at them as power series? And that was our kind of intro to Maclaurin series. So let's see the kinds of questions that you're typically going to be asked to do. So I'm looking at a version of question 1. Imagine that you are told the formula for the nth derivative of some function at 0, and you are told that it is n minus 1 factorial over n plus 1 squared. I'm just making it a little bit different than their question 1. In the first part, you're being asked to create its Maclaurin series. Well, it's the nth derivative at 0, x to the n over n factorial. N equals 0 to infinity, n minus 1 factorial over n plus 1 squared, that's this guy, x to the n factorial. Are we okay with this guy generating these two and then these tagged on? Oops, I'm going to just mute you up. I think I have, yes. So I was saying, are we okay with that becoming this? Now what you need to do here is make it look pretty. N minus 1 factorial will cancel n factorial. What do you get left behind? Now, factorial algebra is a little bit more awkward, so I'll kind of set it up for you. What we're basically doing is finding out what that simplifies down to. Think of that as 1 times 2 times 3, all the way up to the last term. And think of n factorial as being 1 times 2 times 3, and you finish at n. Now, very often you have to figure out what would happen just before n. Wouldn't this be n minus 1? Right, does that now help? What does this cancel down to?
N on the bottom.
And we now have our power series. And the second part of these questions, and I'm typically not going to do the part B, you're going to be asked to find the radius of convergence. So let's show you how that would work. The limit as n tends to infinity of an plus 1 over an. It becomes the limit as n tends to infinity of x to the n plus 1. This guy becomes n plus 1, so you're going to get n plus 2 squared. This guy becomes n plus 1. And then you turn everybody essentially upside down. So you're going to get n plus 1 squared, you're going to get n, and you're going to get x to the n. So en plus 1, upside down version of an. Now there is, as you'd expect, going to be a fair amount of cancelling. X to the n plus 1 cancels most of the x to the n, and you're left with an x on the top, so I'm going to stick it at the side here. I could typically put these guys together and do something, but now and again, not often enough, but now and again, you might get some cancelling first. Can you see anything on the top cancelling anything on the bottom?
N plus 1 and the n plus 1 squared.
If I cancel this one with that, won't you still be left with an n plus 1 on the top? So what do I have here? I have an n plus 1 and an n, and on the bottom, I have an n plus 2 squared. And we're going to do that shortcut. I hope you've seen enough of these guys because they tend to happen like this. What's the limit of that thing going to be eventually as n goes infinite? One. If you have to do it formally, won't you distribute the top, distribute the bottom, divide top and bottom by n squared, or do L'Hopital? End of the day, you get 1. So the answer is that the limit is this guy, which, by the way, is also a very common answer in these questions. And won't it converge when this fella is less than 1? Which means R is 1. So if someone tells you this guy, can't you create the power series, the Maclaurin series, as it's called in these situations? And if you have a Maclaurin series or any other series, can't you find its radius convergence? So there's quite a lot of overlap, like you're doing the same kind of stuff. Any questions about that, or are we go? There we go. Okay. This one is going to be a little same kind of question, but a lot uglier. No, take that later. Don't want to do that one. Okay, we'll do 3. Here is a function. And we're being asked to use our definition, Maclaurin's or Taylor series, to find the first 4 non-zero terms. Now, you'll see this notation. That you're going to do a series centered at 0, at a equals 0. That is Maclaurin. Later on, we will be doing a guy called Taylor series, which is just really an expansion of Maclaurin series, right? A different kind of guy. And in that case, what will happen is that A will be a number. So it'll be centered at 1 or 21. And when you center a number that's not 0, it's called Taylor series. But that's about the only major difference. Right. Now, this is going to be messy. I have to find the first 4 non-zero terms. So I'm going to, oh, okay, I wish I'd give myself more room, but I can do that. F of 0 is 0. Okay. Now, how are you going to differentiate 7x e to the x? What method will I use? Didn't catch that, Jason?
Current rule?
Correct. So make that f, make that g, f dash j plus f of g dashed. You get 7 e to the x plus 7x e to the x, which is what? 7 plus 7x e to the x. And the first derivative at 0 then is 7 plus nothing, which is 7, times e to the nothing, and that's sort of 7. Should tell you that these questions are going to be long. Now, if you want to get the second derivative, don't you just differentiate this fella? Great. And I'll call this f, I'll call this j, and I get yet another one of these fellas. And differentiating this guy gets you 7. This guy is e to the x. Leave this guy alone. E to the x. And now I'm going to get 7 plus 14x e to the x. And the second derivative evaluated at 0 is a rather boring 7. Now,
Why be 14 plus 7x?
oh, thank you. Thank you. And 14 plus 7x gets me 2 lots of 7, 14. I could find the third derivative and then find the fourth, but I'm going to see if I can cheat. 7 plus 7x, 14 plus 7x. Do you think the next one is going to be, just looking at patterns? 7 plus 7x, 14 plus 7x. What would the next one be?
21 plus 7x.
And it actually is. Which means the third derivative is 3 times 7, 21. And the next one is going to be, trust me, 28. And so the fourth derivative at 0 is 4 times 7, which is 28. And they only want the first 4 terms of the Maclaurin series. Now, if you look at this guy here, right, and you expand it out, let's do that on the next page. If you take any function and you write down what it looks like as a Maclaurin series, but if you write it down 0, 1, 2, 3, 4, and so on, you get the 0th derivative at 0, x to the 0 over 0 factorial. That's always weird looking. Then you get the first derivative at 0. Then you get the second derivative at 0, x squared. And then you get the third one, and then you get the fourth one. So here goes. The 0 derivative at 0, do you know that is just the value of the function at 0? That's what you define the 0th derivative as, right? Basically, you haven't differentiated it at all. And this guy is 1, this guy is 1, and this guy is 1, so you get 1. Except, I take that back, isn't this guy 0? So you get 0 times 1. Now the next one is 7, x over 1 factorial. The next derivative was 14 x squared over 2 factorial. The next one is 21x cubed over 3 factorial, and the last one was 28x to the 4 over 4 factorial. And because this is 0, you need the first 4 non-zero terms. Do you think that's the answer, or can we make it prettier? Okay, well, that's definitely 0. 1 factorial is 1, so that becomes 7x. What number is 2 factorial?
2.
So 14 over 2 gets me 7x squared. 3 factorial is 6, right? 1 times 2 times 3. 21 over 6 becomes, cancel a 3, 7, 7 halves. And 4 factorial is 12. Is it 12? 1, 2, 3, 6. It's 24. And 24 over 28 cancels down as I'm not going to risk that. If you take
7/6.
thank you. Okay, that's as good as it's going to go. So the question asked us to write down the first 4 non-zero terms of the Maclaurin series. And you could see how much work we had to do. We had to find a whole load of derivatives evaluated at 0, so we could put a number here. And then we write down all the terms that we have until we get to 4 answers that don't have zeros in them, and we'd stop. If they wanted the first 3 non-zero terms, wouldn't we write just that? Now here's a question they didn't do, but I think is worth doing. Do you notice here, and I'll write them down, the first derivative was 7, the second derivative was 14, but I'm going to write it as 2 times 7. The third derivative was 21, and the fourth derivative was 28. There is a pattern here. What is the nth derivative?
N times 7.
Agreed. N, right? 4 gets you 4, 3 gets you 3, n times 7, which I'm just going to call 7n because it looks nicer, right? If you can find that guy, if you plug that in here, don't you now have the Maclaurin series? 7n x to the n over n factorial. And that function was actually 7x e to the x. Style points are important. Is there anything you can do to this? Actually, there is. What can you do to this to make it just a little bit prettier? Now, I don't know if we've ever done this yet. We've cancelled factorials with other factorials, but I don't think we've ever cancelled an n on its own with a factorial, but it can be done.
Doesn't it cancel to make the bottom n minus 1 factorial?
It does indeed. And let's show you how that happens. You get an n on the top, that's all you got. You get an n factorial on the bottom. It's always a good idea to write the one just before the end as well, as I have here. If you cancel those out, don't you have a 1 on the top? And 1 times 2 times 3, but finishing on n minus 1 is n minus 1 factorial. So do you see the algebra of factorials is kind of unique to itself? You know, the way you deal with factorials cancelling is It's kind of different from a typical cancel. That means I now have the power series, which is unique. That's the only power series for 7x e to the x. That's remarkable that it's unique as well. There's only one answer, and that's it. And if I gave that question to someone in Korea or to Nigeria or wherever, they would still come up with that same answer. Which tells us in mathematics that functions can be thought of as power series. And we just give labels to some power series because it's helpful. Isn't it helpful to call something e to the x rather than a big ugly sigma thing? But for all respects and purposes, don't they behave as if they're the same? It's quite interesting insight. Oh, side issue, because I want to. Maclaurin, very interesting mathematician. Do you know what nationality he is or was?
Is he Scottish?
He is. And a very, very, very good mathematician. He did not teach at my university, Glasgow University, as a professor, but he was a visiting professor to my university. So he did come to my university. So pretty cool guy. Quick summary of his life. He was what you would call today a child protege. Do you know those people you see now and again who finish high school at 9 and go to university when they're 10 and graduate when they're 14 and become a doctor when they're 17 or 18? You know, one of those kind of, he was one of those. But he was a child protege where it was virtually unheard of to be a child protege, right? People wouldn't even have thought of it as a thing. You know, today we know it happens, so you see it, but even today, isn't it very rare? You know, somebody who can finish high school when they're 10, right? That doesn't happen every day, right? There's probably somebody in America right now who's done that, but it's very rare, right? So he was a child protege and he went through the same thing. He got his doctorate when he was, I think he was 17. And you couldn't shorten your doctorate. You had to do it in 2 years. Even if you were really bright, it was a 2-year thing. You had to do it, right? Because part of it, at least in those days, part of it was research, and you had to do some research, and your research couldn't be published unless you'd spent at least X amount of months doing it and so on. So he probably could have done it in less time than that. And he became a full professor when he was 18. He started teaching mathematics. And one of the universities he taught at was Glasgow University. That is a pretty unique person. And I diverge, but he is Scottish and he is bright and he went to my university, at least as a professor. So I think that is worth sharing, right? To which I could say to most of you, tell me a half-decent professor from UW who's as famous as that. And since we're on the bragging stage, my university, for instance, has got a big iron rock gate, and on that iron rock gate, they have the names of very famous people. So to give you an idea of one of our famous professors, is we have a professor called Kelvin. And if you're in physics, you know degrees Kelvin. That's my guy. How many people in UW, professors, have anything like that named after them? Can you see how arrogant Scottish people can be? Right, let's go. We've got another one I want to try out here. This one is question 4. Here is a function, the natural log of 1 plus 3x, and we're being asked to create the Maclaurin series for it. So in other words, we need to find a formula for the nth derivative at 0. So I'll start off with f of x. If you plug in 0 for x, f of 0 is the log of 1, which is 0. If you differentiate this fella, you'll get 1 over 1 plus 3x times 3. And if you evaluate this at 0, you will get 3. If you do the second derivative, and you're going to just have to trust me on here, you get negative 9, but I'm going to call it negative 3 squared over 1 plus 3x squared. And if you evaluate this at 0, you get negative 3 squared. It is a good idea when you do these questions not to do the calculation. So if the answer is 9 and you got it by 3 times 3, it's better if you leave it like this. So I'm now going to tell you what the third answer is at 0. And I'm going to tell you the fourth derivative answer at 0. And if you see a pattern, which eventually you have to, or you're not going to be answering this question, we should be able to figure out this guy. And if we figure out this guy, I just pick it up and I stick it here and we're finished. So, first derivative gets you 3. Third derivative gets you 3 cubed. Fourth derivative gets you 3 to the 4. What would the power of n for the nth derivative be?
It's 3 to the n, but would we also have a negative 1 to the n since it's alternating?
Yes, which was going to be my second bit. I just broke into 2 pieces. So now we're going to look at plus, minus, plus, minus. Whenever you get a plus, minus, there are 2 guys in the world you're going to have to pick. It's either n or n plus 1. Because, you know, the alternating could happen at a different stage, right? The plus, minus, but it could go minus, plus, then minus, plus, right? It could alternate. So just pick one of them. The fourth derivative is negative. You see that? The fourth derivative is negative. If you plug in 4 here, would that get you a negative 1? No. Would this get you a negative 1? Right, negative 1 to 5. So that tells me to use this fella. So our question was, find the Maclaurens for this function. It's from n equals somebody to infinity. And where are we going here? The nth derivative at 0, x to the n over n factorial. This fella is negative 1 to the n plus 1, 3 to the n, x to the n over n factorial. So far, so good. Agreed? Right. Now, you might think that's just me being careless and not putting 0 in. Let's see why that may or may not be 0. Isn't the function at the start of its life, the first one, 0? So won't f0 brackets 0 be 0? I don't want that guy. If the first term is 0, you don't want to use it. Well, you might say, well, what's wrong with me putting in 0 here? Well, let's try it. If I put in 0 here, won't I get negative 1 to the 1, which is negative, 3 to the 0, x to the 0 over 0 factorial? But doesn't that get me the number negative 1? Do you see it doesn't work? It works for everybody else, but it doesn't work for the first term. So if you're doing a Maclaurin series and the first term is 0, start at 1 and then use your pattern. I haven't seen it, but I guess it could happen. Can you imagine a question where the first 2 guys were 0 before you started getting numbers? Then you would start at n equals 2 if that happened. That's just a little quick, easy to, easy to not do. Actually, I'm looking at question 4 and they told you it was 1. So even if you didn't know to start at 1, it did 1 anyway. But that's what you should have done. Okay, this is a good point to say hi for attendance.